Welcome. My name is Ashraf Mahgoub, and today I will present WISEFUSE, Workload Characterization and DAG Transformation for Serverless Workflows. This work is a collaboration between Purdue, Carnegie Mellon, and Microsoft Research. Serverless computing is becoming increasingly popular. It's an attractive model in which users focus on writing the code for their functions, while the platform deploys and executes the function. Also, users pay for exactly the execution time of their function and the amount of resources the function uses, which is known as the pay-as-you-go model. And to give a quick example for serverless function, we show here our function classify that simply takes a frame as input and produces the object detection result for that frame. And in order to build an application in a serverless platform, users can compose several functions together in a form of a chain where functions are executed in series, and the output of one function becomes the input of the next function. For example, here we have a chain of 3 functions: split, extract, classify. And we can also organize the application in a form of a DAG, where we can have a degree of parallelism in one or more of the execution stages. Here we have parallel extract invocations and parallel classify invocations in this DAG. So what is happening in this DAG is that the split function takes an input as a video, splits it into 30 chunks, and for each chunk we have an extract that extracts a representative frame, and then a classify that detects the objects in that frame. And the DAG latency here is estimated as the time between start and end states where all the functions finish execution. In current serverless platforms, this DAG will be executed as each function in a separate VM, and hence it will use a total of 61 different VMs. And also users have to specify what is the VM size for each function, and that impacts the amount of compute resources that is assigned to each function, and hence will impact the end-to-end latency and the cost of the DAG. We identify 2 performance bottlenecks due to running each function in a separate VM. The first is high communication latency between in-series functions. For example, when we pass the extracted frame from extract function to classify function, and also high computation skew among in-parallel invocations. And for that, consider this example of 2 parallel classify invocations. One of them operates on a frame with few objects, and therefore it has a short execution time. The other one operates on a frame with many objects, and therefore it has a longer execution time and it dominates the stage's latency, for which we will have to wait for the longer execution before we start the next stage of execution. To understand the impact of these 2 performance bottlenecks, we analyze real workload traces from Azure Durable Functions. We show a figure for depth, width, and total number of functions within the DAG. The x-axis is on a log scale, and the corresponding CDF on the y scale. We also give an example of our definition of DAG depth and DAG width on the right side. We notice that the DAG structure is wide and shallow, so the maximum width can grow up till 10.9K, but the maximum depth is only 47. Next, we study the DAG invocation frequency. And in this figure, we are showing the DAG rank on the x-axis on a log scale, and the corresponding invocations per day on the y-axis, also on a log scale. We notice that very few DAGs constitute the majority of all DAG invocations. Specifically, the top 5% most frequent DAGs constitute 95% of all DAG invocations, and those DAGs have a high invocation rate of 1.6K per day. Next, we study the impact of the 2 performance bottlenecks that we described on the DAG's latency. First, we show how the intermediate data size that is being transferred between in-series functions impacts the latency on this figure. We show the end-to-end latency of the DAG on the x-axis on a log scale, and the corresponding CDF on the y-axis. we noticed that DAGs with intermediate data size of 1 megabyte or more have 9.5x higher median latency than DAGs with less than 1 megabyte of intermediate data. Similarly, we study the impact of computation skew between in-parallel invocations. And here we also noticed that DAGs with a skew of 100 or more have 17x higher median latency than DAGs with a skew of less than 100. Now it's a good time to define the first optimization that we apply, which is fusion. And fusion's target is to minimize the communication latency between in-series functions. So if we have two functions that are deployed in separate VMs, the only way we can communicate data between them is through upload and download operations from a remote storage, which can add significant latency to the DAG. However, if we fuse the two functions together in the same VM, now we can leverage local data passing between the two functions and reduce the DAG latency. However, fusion has two challenges. First is, in a chain of serverless functions, which pair of functions should we fuse? And also, when the functions that you are fusing together have different resource requirements, what is the additional cost that we have to pay for that fusion to happen? Next, we define bundling, and bundling helps with mitigating the computation skew between parallel invocations. For example, assuming that we have two parallel invocations of classify, one of them is a short invocation that takes only 6 seconds, and the other one is a straggler that takes 12 seconds. We notice that the straggler dominates the end-to-end latency, and with bundling, what we do is we execute the two functions together in a VM with double the size. What happens is after 6 seconds, the short-running invocation will finish execution and release the resources. And accordingly, the straggler will have access to additional resources, which will allow the straggler to finish the execution faster and minimize the end-to-end latency. However, with bundling, we have a challenge of what is to use as the bundle size. For example, we can run each function in a separate VM. That is a bundle size of 1. We can run pair of functions together in the same VM. That's a bundle size of 2. Or we can bundle all functions in the stage together in just one VM. The different bundle sizes impacts the latency of the stage as well as the cost of the stage. Now, to summarize the main insights that we have seen so far, first, we apply workload characterization on Azure Durable Functions. And from the characterization, we identify that there are very few DAGs that constitute the vast majority of DAG invocations. We also studied the serverless DAGs structure, and the structure of the DAGs show that they are usually wide and shallow. We have proposed two important optimizations. One that is fusion, which runs in-series functions together to minimize the communication latency between them. And the other one is bundling, which runs in parallel invocations together in the same VM so that we can mitigate the computation skew between them. Next, we describe the design of WISEFUSE. The first component of WISEFUSE is the DAG profiler, which accepts a DAG as an input from the user and profiles each function in the DAG as well as the entire DAG to capture the execution CDF of the DAG. We represent the execution time of each function as 3 components: download, then processing, and then upload. Next, we apply the DAG modeler, and the DAG modeler builds a performance model for every function in the DAG as well as the entire DAG. The modeler takes into account 2 types of correlation: the correlation between in-series functions when it performs convolution, and the correlation between in-parallel invocations when it performs max of their CDFs. We use these 2 operations to estimate the latency for every component in the DAG, as well as the entire DAG when we estimate the impact of either doing fusion of 2 stages or doing bundling of 2 parallel invocations. Third, we apply the DAG transformer, and the DAG transformer identifies which stages should be fused together to minimize the communication latency between them, and which parallel stages that experience high computation skew and hence can benefit from bundling. Finally, we apply the optimizer that uses both fusion and bundling to generate a new execution plan for the user-defined DAG, and that execution plan describes which stages should be fused together, what is the bundle size to use in each parallel stage, and what is the VM size to use for each function or a function bundle in the DAG to meet a user required latency target with the minimum cost. Here we show the end result of our optimization for the video analytics application example that we have seen before. On the left side, we have the user provided DAG that requires 61 VMs to execute the functions in the DAG. However, on the right side, we have WISEFUSE optimized DAG that requires only 6 VMs to execute the DAG. Specifically, WISEFUSE decided to fuse split with all extract invocations in just one VM. However, it decided to keep extract and classify separate without fusion. However, it decided to bundle classify frame invocations into bundles of size 5 to minimize the computation skew between them. Now we move to the evaluation of WISEFUSE, and WISEFUSE is deployed with AWS Lambda and tested with 3 different applications. First, we noticed that the profiling that WISEFUSE requires is both fast and cheap. Specifically, with 300 profiling runs, WISEFUSE achieves a low error in the P95 end-to-end latency estimation that is less than 13%. It also achieves low error in estimating what is the impact of doing either fusion or bundling, that is less than 7%. And recall that the majority of all DAG invocations belong to a very small subset of the most frequent DAGs. And these most frequent DAGs have a very high invocation rate, allowing us to profile them very quickly and with a low cost. Next, we compare WISEFUSE to baselines and related works. For baselines, we compare to the user-provided DAG when we assign the maximum VM sizes so that we achieve the lowest latency, or if we assign the minimum VM sizes to achieve the lowest cost. We also compare to related works such as Sonic, Photons, and Fastlane. And finally, we show how WISEFUSE adjusts its execution plan according to different latency settings. First, compared to user min and user max, we notice that WISEFUSE has 63% lower cost than user max, and also 61% lower P95 latency than user min, showing that WISEFUSE execution plan achieves the best of both baselines. Next, we compare to Sonic, and we notice that WISEFUSE achieves 47% lower latency than Sonic. This is because Sonic focuses on fusion only to leverage data locality, but it does not perform any bundling, or it does not take the latency distribution into consideration. Compared to Photons, WISEFUSE achieves 62% lower latency, and this is because Photons performs bundling only, and bundling there is performed to minimize the memory utilization. However, it does not adjust the bundle size to meet different latency targets, and it does not also mitigate communication latency between in-series functions. Also, WISEFUSE achieves 39% lower latency than Fastlane. Fastlane uses a fixed bundle size of 6 workers that matches the number of virtual CPUs that can be achieved in AWS Lambda. And again, Fastlane does not perform any fusion or any other technique to mitigate communication latency between in-series functions. Finally, we show 3 latency targets for WISEFUSE, and we show that the higher the latency target we set for WISEFUSE, it is able to achieve a lower cost with a better execution plan. And none of the baselines or the related works have that ability to adjust the execution plan based on the latency target to achieve a lower cost. In conclusion, we have seen workload characterization for serverless DAGs in Azure Durable Functions. We identified two important optimizations. One that is fusion to minimize communication latency between in-series functions. And second one is bundling to minimize computation skew between in-parallel function invocations. And WISEFUSE applies these two operations, fusion and bundling, to find a better execution plan that meets a user-defined latency objective with a low cost. Through experimental evaluation, we have shown that WISEFUSE model answers lots of what-if questions, such as what is the impact of fusion or bundling, and what would be the impact if we change the bundle size. And accordingly, WISEFUSE generates different execution plans that meet different tail latency targets with different costs. With that, I conclude my talk. I will be happy to answer any questions. Thank you.